So for these classifier theorems, you'll find the proofs in the description of the video. Basically, our first theorem tells us what happens when we pull back true along an arrow, and our second theorem says how we can find a subobject classifier. So these between them really tell you everything you need to know, but like I say, I've kind of explained things in sort of general enough terms to be able to prove it. And, I sort of encourage you to hang on for some practical examples because it's much easier once you see a few examples of how this stuff works. Anyway, here's the idea. So classifier theorem 1. Suppose we have an arrow. So obviously we're working in sets to the power of c. And suppose we have an arrow little a from capital A to omega. And now we're going to suppose that A star is the pullback of true along A, or if you like, it's the inverse image of true along A. So, we could write it as A to the minus 1 of t, if we like. And we're thinking of this as being an inclusion monic. Now, what this result says, we're thinking of this as being an inclusion monic, so really it's a natural transformation, but the components of this natural transformation are just inclusion functions, so it's really the form of this object Q that's the important thing. And we're saying that the E-type figures of Q consist of the set of theta in A of E, which is such that AE of theta is equal to psi E t. Okay, so this is really important. Essentially what we're saying is that if you have a classifying arrow, so you have an arrow little a into omega, if you want to sort of find out which subobject that classifies, in other words, if you want to find out little a star, well, just look at omega, look at its E-type elements. Amongst those, you'll find psi et, that's the kind of E-type element of omega, which corresponds to this kind of maximal subobject of Hom E, blank. Now, what you just do is you just look at all of the stuff in A that's getting sent to things like that under little a, and that's the stuff that's going to be present in this subobject Q. Okay, in that subobject A star, which is an inclusion monic from Q. Okay, that's basically what this is saying. So essentially this allows you to work out the pullback along essentially this allows you to work out which subobject is being classified by a particular arrow into omega, at least up to equivalence, but that's all you can really do in topos theory. But for us, we like to represent our monomorphisms as inclusion monics. And given any kind of class of equivalent monics, there's always a kind of unique equivalence. There's always a kind of unique inclusion monic, which they're equivalent to. So it gives us a kind of canonical representation of these kind of sets of monics. It gives us a kind of canonical representation of this kind of bunch of equivalent monics. We can just say, okay, a good representative of it is an inclusion monic. Anyway, this is the result. I'm not going to pause too long on it now because I think it's better I get to some examples where you'll see these ideas more clearly, but just note that, the proofs of this stuff are in the description to the video if you want to dig more deeply into this stuff. Okay, our second classifier theorem then, this tells us how we can actually find the classifying arrow of a particular monic. Okay, so suppose, again, obviously in set to the power of c, we have a monomorphism M from an object X to an object A, and we want to find chi of M. we want to find this arrow chi of m from A to omega, which is the classifying arrow of m. So this theorem explains how to do it. So formally then we say that the statement of this theorem, we don't just describe this classifying arrow. Essentially, it's this result which really establishes that we do have a sub-object classifier, because in this result, we're not only describing what chi of m is, we're proposing that it's unique, which essentially means that we have a sub-object classifier. So formally then, we're saying that this kind of inclusion monic from our terminal object to omega, called T, which I've already described, this kind of truth arrow, that together with omega does comprise a sub-object classifier of set to the power of C. And moreover, if we have a sub-object M of A, so this monomorphism M from X to A, then its classifying arrow is going to be this arrow chi of M from A to omega. And how is this defined? Well, for an object E of our category C, suppose we have theta in A of E, so we suppose we have an E-type element theta of A, well then we define chi m of E of theta to be the element of omega of E, which is going to correspond to the inclusion monic, which is the pullback of M along theta under arrow. Okay, so this is a little bit cryptic, but then again, sub-object classifiers are pretty complicated. And also, it's also true that obviously this chi m is the unique arrow from A to omega with this property. It would have to be for this thing to be a sub-object classifier. I mean, that's one of the kind of requirements we have of a sub-object classifier, is that, given any monic, there's just a unique arrow from the kind of target of that monic into omega, such that pulling true back along that kind of classifying arrow gives us back our monic. Anyway, what does this mean? This is confusing, right? Well, firstly, remember about omega of E. Omega of E is the set of E-type elements of omega. But remember that we're thinking of the kind of elements of omega of E as sub-objects, in fact, inclusion monics of Hom E comma blank. You remember we sort of saw that they're going to correspond to such things, and then we agreed that we're going to actually consider the E-type elements of omega as sub-objects of Hom E comma blank. And so what that means is that an element of omega of E, for us, we sort of simultaneously think of such a thing as a sub-object of Hom E comma blank. In fact, an inclusion monic into Hom E comma blank. And so when we do the ETH component of chi of m on this theta, that's obviously going to give us an element of omega of E. And so, in other words, we can think of chi m of E of theta as a sub-object of Hom E comma blank. And how do we get this sub-object? Well, all we do, we take our theta, Well, all we do, we take our theta and then we kind of find the natural transformation corresponding to it under the Oneida correspondence. And that gives us an arrow theta under arrow, which is going to be an arrow from hom e comma blank into A. And then we also, of course, have this subobject M of A, and then we just pull back M along theta under arrow, and this is going to give us this kind of subobject here of hom e comma blank. This is what we call theta under arrow to the -1 of M. And we just consider this to be the result of doing the ETH component of our classifying arrow on theta. Okay. So that's basically what there is to it. Now, I do think that this is a little bit difficult to wrap your head around at first viewing. So, as I say, let's look at some examples, and then, you can come back and have a look at the sort of proofs of this, and then it's going to become a lot more clear.